In this segment on gases, we're going to take a look at effusion and diffusion and the movement of particles in the gaseous state. All right, so effusion and diffusion involves the movement of gas particles. So here we have the formula for the root mean squared velocity of a gas particle, the u here. Now again, what we'll do is we'll pretty much, at this level, we'll be able to equate the root mean squared velocity to the straight velocity. If I rearrange this and do the velocity is equal to the square root of 3RT times 1 over the square root of the molecular mass, we can see that the velocity is inversely proportional to, or is equal to a constant times 1 over the square root of the molecular mass. So this is assuming two gases are at the same temperature. What this means is that the larger the molecular mass would be, the slower the velocity would be. So when you look at the picture in the graph here, so all of these different types of substances, molecules of these, are at the same temperature. And so again, on as we did with the kinetic energy distribution curve, we look at the vertical y-axis as being the fraction of the molecules with a particular speed, and across the x-axis is a molecular speed. And you can see that the larger molecule, the O2, which has a molar mass of 32, would in general have a smaller or a lower average speed than, say, a hydrogen, which has a molar mass of 2 grams per mole. So it just shows you that relationship between the molar mass and the speed. The larger the mass, the lower the speed of the particles. First, let's define effusion and diffusion. So the effusion is the movement of particles through a hole in a container. So the movement of particles through a hole in a container, whereas diffusion is the movement of particles from an area of high concentration to an area of low concentration. So movement of particles from an area of high concentration to an area of low concentration. So this could be, for example, the diffusion of perfume through some space. You would be able to smell the perfume because it diffused from the person's body through the air to you. So that's diffusion. Effusion would be thinking of if you had a small hole in the balloon, and the air inside the balloon would effuse out of that hole in the balloon. Now, from a quantitative standpoint, if we take two gases that are at the same temperature, which means that they're going to have the same kinetic energy. So we put our kinetic energy formula up here. So two gases at the same temperature would have the same kinetic energy. So we would have 1/2 the mass of the first gas times the velocity squared of that first gas would equal to 1/2 the mass of the second gas times the velocity of that second gas squared. And a little mathematical work with this, we can cancel out the 1/2s. And let's move the velocities over to the left. So we would have the first velocity squared over the second velocity squared is equal to the mass of the second particle divided by the mass of the first particle. And then if we take the square root of each side here, we end up with the velocity. In this case, we're going to look at the rate, to call it the rate of diffusion. So we're going to say the rate at which gas 1 diffuses compared to the rate at which gas 2 diffuses is equal to the square root of the mass of the second particle divided by the mass of the first particle. And of course, we can, since mass is going to be directly related to the molar mass, we can make that equal to the square root of the molecular mass of the second gas to the molar mass of the first gas. So again, this is a rate of diffusion. Now, we'll find other things that we can plug into this equation as well. If we're talking about perhaps the distance that is traveled, if we think a little bit about rate, what rate of travel, rate of speed is, your rate is equal to the distance traveled per amount of time. So if we were going to try and find the relationship between how far one gas would go compared to another in the same amount of time, our time part would be constant, and our distance would then be directly proportional to the rate. So we could actually do another relationship here where distance traveled for gas 1 compared to distance traveled for gas 2 could be plugged in there. We could also look at a standard distance. So suppose we had 2 different types of perfume, and we were looking at how fast one perfume got to across the room compared to the other. So that in that case, we'd be looking at not the time, or excuse me, we would be looking at the time, but the distance would be constant. So in that case, the rate would be inversely proportional to the time. So we would flip things over then. So we'd have the time that the second gas diffused divided by the time it took for the first gas to diffuse. So we'd have something like that. If we were looking at, for instance, in the picture above here, where we had the particles escaping through a small hole in a container, the reason they would escape through the hole in the container is because they were hitting, the particles would hit that part of the wall, that section of the wall of the container. And so obviously the faster it's moving, the more particles that would escape. So we could actually do another variation on this and say that the number of particles of gas 1 that escape through the container divided by the number of particles of gas 2 that escape through the container would also be equal to the square root of the molecular mass 2 over molecular mass 1. So all of these things can be used for various different problems involving diffusion and effusion. So we'll see a bunch of practice problems with this in our homework and our classwork.